All right, we have a couple more examples to look at in this section. So in this example, we're going to sketch the function y equals the natural log of x over x squared. So to get us started, just like the other examples, we're going to look at the domain first. Now in this case, the domain is actually going to be entirely determined by the natural log function right here, because the natural log is only defined for positive real numbers. That would also exclude 0, which is also it's also where this function is not defined, because we'd also be dividing by 0, but the natural log sort of takes care of that. So the domain is the interval from 0 to infinity. Okay, now next up, we want to look at intercepts. Okay, so starting with our x-intercepts. We would set y equal to 0. 0 equals the natural log of x over x squared. However, we set y equal to 0, solve for x. This would require the natural log of x to equal 0. So I can say that this implies that ln of x equals 0. Taking e to the power of both sides would give me x equals 1. So I have an x-intercept at 1, 0. I don't have a y-intercept because that would require me to plug a 0 in for x, which we know is not in the domain of our function. I don't think any of our functions have been defined at 0, I'm realizing. The next function will be, so none. All right, next up, symmetry. Once again, there's no symmetry in this function. We can't have symmetry because we're only defined for positive numbers anyways. Remember, in order to get symmetry, even or odd symmetry anyways, you have to be able to plug a negative x in for every x in your domain. So since we can't do that, there's no point in checking symmetry here. Next up, after symmetry, we look at asymptotes. Does this thing have any asymptotes? Okay, so I want to look at the limit as x approaches infinity of this function. So as x approaches infinity, we're looking at horizontal asymptotes here. Horizontal. If I look at the limit as x approaches infinity of the natural log of x over x squared, both the numerator and denominator go to infinity. So what that tells me is that this is an infinity over infinity indeterminate form. That means I can apply L'Hopital's rule to try and evaluate this limit. This will be equal to the limit as x approaches infinity of, take the derivative of the numerator, 1 over x, derivative of the denominator, 2x, which is the same thing as the limit as x approaches infinity of 1 over 2x squared. Now I have a constant in my numerator and a denominator that's going towards infinity, which takes the whole thing to 0. So that tells me I have a horizontal asymptote at y equals 0. How about a vertical asymptote? Okay. Well, the only place it would make sense for there to be a vertical asymptote would be at 0, because this function is defined for all positive real numbers, and it's not defined for any negative real numbers. So the only question is, as we approach 0 from the right, is there a vertical asymptote there? What is the limit as x approaches 0 from the right? So plus there. Okay. Now what's happening with our function? So we have the natural log function on the top, ln of x over x squared. The natural log of x is going to approach negative infinity as x goes to positive or to 0 from the positive side. We know that from the natural log function. The denominator is going to be approaching 0, and it's going to remain positive the entire time. So I have a very large in absolute value negative number over a very small positive number, this is going to go towards a very large in absolute value negative number, which means this is going towards negative infinity. So I do have a vertical asymptote, and we're moving towards negative infinity as we approach 0 from the positive side. That's what that asymptote is doing to our graph. That takes care of asymptotes. Now we look at increasing and decreasing. Okay, so we need a derivative here. Y prime is equal to what? I need to use my quotient rule for this. So my denominator times the derivative of my numerator. That'd be x squared times 1 over x, which is just x, minus the top function times the derivative of the bottom. That would be 2x natural log of x all over x squared. My denominator squared. That's x squared squared, or x to the 4th. Notice I have an x in all of these terms, which I can now cancel. That becomes a 1, that becomes a 3. So I have 1 minus 2 times the natural log of x over x cubed, and we want to set that equal to 0 to look for critical numbers. Okay, this is only going to equal 0 if my numerator is equal to 0. So this means 1 minus 2 natural log of x is equal to 0, or equivalently, the natural log of x is equal to 1/2, so that x is equal to e to the 1/2 power. Now I'm going to approximate this one because, again, even though most of the time we ask for you to leave numbers in either exponential form or radical form or whatever, we are going to use decimal approximations here so that we can figure out exactly where this would go on a graph. Without that, it's really difficult to know where that is as far as how everything is spaced out. So 1.649 is an approximation for that. Okay. So what we have here is a critical number, and I need to go to my, excuse me, my number line here to check that critical number. So e to the 1/2 is my critical number, and that's the only one that I need to check here. So I'm going to put a 0 here, because that's just to remind me that I can't go any further to the left, simply because I have a domain restriction here. So that's still 2 intervals, these 2 guys right here. If I pick something to the left of e to the 1/2, since e to the 1/2 is approximately 1.649, I could plug a 1 in. And if I plug a 1 into my derivative here, I'm going to get 1. I get something that's positive. So it looks like f prime of x, I'm calling it f prime. I should be calling it y, but that's okay. F prime of x is positive here. If I plug in a negative number, sorry, not a negative number, something to the right of e to the 1/2, maybe 2, because that would work here, you're going to see that your derivative comes out negative. So I get f prime of x is less than 0 there. Okay, so we are increasing on the interval 0 to, I'm going to use my approximation here, 1.649, decreasing on 1.649 to infinity. Okay, now for my local max and min. Once again, I use my first derivative test. I only had one critical number, and we go from increasing to decreasing, so it's something like that. So this value here, e to the 1/2, or 1.649, is going to be where my maximum occurs, my local maximum. I'm going to say local max of. Now I would need to plug 1.649 into the original function here, or e to the 1/2 power. Either way, you're still getting a decimal approximation there. This one comes out to approximately 0.184, and it occurs at x equals e to the 1/2, or 1.649. Okay, so that represents a point. Local maximum is a point on my graph that I'm going to put on there when we get to the graphing step. Okay, that was the only critical number. It's the only local max or min that I can find here. So we keep moving on to concavity and points of inflection. So concavity and points of inflection. We need our second derivative now, so y double prime. Okay, y double prime, if I take, where's my first derivative? This guy. Okay, I'm using the quotient rule on that again. So bottom function times the derivative of the top, that's x cubed times, what's the derivative of this? This would be negative 2 over x. So negative 2 over x minus this function times the derivative of the bottom, 3x squared times 1 minus 2 natural log of x. All over my denominator squared, which would be x to the 6th power. And then I get a cancellation again. I can cancel x squareds out of this. So I can cancel this x squared. This would become a 4. This x right here, this x cubed is going to become an x squared. And then beyond that, I can cancel this x with that x. So this whole thing simplifies down by quite a lot. I get negative 2 minus 3, which I'll go ahead and distribute in here. That becomes negative 3 times 1, which is just minus 3. Negative 3 times negative 2 natural log of x would be plus 6 natural log of x over x to the 4th. If we set that equal to 0, that just simply means my numerator would have to equal 0. So simplifying this a little bit more, this would imply this becomes negative 5 plus 6 natural log of x equals 0, which means that the natural log of x here is equal to 5/6, or x is equal to e to the 5/6 power. And once again, we're going to want an approximation there. So e to the 5/6 power is approximately 2.3. Okay, we want to see if that represents a point of inflection. And once again, put a 0 here just to kind of set a boundary. This is e to the 5/6 power right here. And that's 2.3 roughly. So if we pick a number between 0 and 2.3, say 1, plug that into your second derivative, which after simplifying looks like this, or negative 5 would be even simpler. But if you were to do that, you're going to see that your function is, what did I say this was, 2.3? The function is concave down there. It's negative. It has a negative second derivative. And pick a number larger than 2.3, say 3. And you get a positive second derivative. So we're concave up there. That makes this a point of inflection. So I have concave up on the interval from e to the 5/6 power, which we're going to say is just 2.3, to infinity, concave down on the interval from 0 to 2.3, and we have a point of inflection at 2.3, and then again we need a y coordinate for that point, so we would take that point, but use e to the 5/6 power for accuracy, plug it back into your original function, and you're going to have to round once again. So this comes out to approximately 0.157. Okay. All right, now we have a whole lot here, so we're going to try and graph this thing. I'm going to set up my coordinate axes this way. Since my function is not defined for negative real numbers, I don't need anything to the left of that y-axis, so might as well give myself more space on the right side. Okay, so we have addressed the domain already. The only x-intercept in this guy is 1, 0, so I need to make sure that I have an x-intercept occurring right there. There are no y-intercepts. For my asymptotes, we should have an asymptote at y equals 0. That is the x-axis. So we just need to remember that. That's going to be an asymptote. We also have a vertical asymptote at the y-axis, x equals 0, and our function is supposed to be approaching negative infinity there. So we know we're going to be going like this somehow. And then to the right, we know that our function is going to be either this way or that way, approaching the x-axis. Okay, what else do we know? increasing and decreasing. We know that we are increasing on the interval from 0 to 1.649. So I'm going to notate that. Where is 1.649? 1.649, we're going to say is roughly there. We're increasing that whole time. Increasing that whole time. And then we decrease past that. Okay? This is also going to be a critical, or it's going to be where we have a local max occurring. The local max occurs at 0.184. That's going to be really, really close to the origin here, or the x-axis, 0.184. So we should have a point around there somewhere, and that's going to be a local maximum. Okay? And then what else do we know? We are increasing up until that point and decreasing away from that point. Concavity and points of inflection. We have a point of inflection at 2.3, 0.157. So let's notate that one as well. 2.3, let's maybe put that out here. 2.3, 0.157 is going to be so close to that guy. I'm gonna go like this. 0.157. It's going to be so close that I can't really squeeze it in very well. So there's going to be a point of inflection right here. We know that we are concave down all the way up to that point and concave up away from it. So here's what I'm thinking our graph is going to look like. We know this is a vertical asymptote and that we're concave down all the way up to 2.3 and that this is a local maximum at 1.649. So we're going to do something like this. We know that that's an x-intercept. We hit a local maximum here. Then we come down to this guy. We're still concave down this entire time, but then this is a point of inflection. We switch to concave up. So it's going to start to kind of curve a different way and be concave up from there. This is also a vertical or horizontal asymptote, so we're not going to cross the x-axis. We're just going to go like that. Okay? Not a good hand sketch, but it's got the detail that we need in there, so we're going to be satisfied with that. All right, one more to go. Before we can do this last example, we need to talk about slant asymptotes. You may have talked about slant asymptotes in college algebra class or pre-calculus class. We're going to define them in terms of limits. So basically what a slant asymptote is an asymptote that is a line that is neither vertical nor horizontal. So it has a slope, a non-zero slope specifically. This is an example of one. This red line has the equation y equals mx plus b. That's slope-intercept form. In this function, the blue curve, as x approaches infinity, this blue curve is going to be coming closer and closer to the red line, which makes it like an asymptote. But we call it a slant asymptote because we think of that slope as giving a slant to that line. Now, if you want to define a slant asymptote, mathematically speaking, we can use limits. So what we would do is we would say that f of x minus mx plus b, in parentheses there, which would be the vertical distance between this function and the line that we're suggesting is an asymptote. We want that distance to shrink towards 0, which indicates that these two the curve and the line are getting closer and closer together. So this difference represents that distance between those two functions, and taking the limit as x approaches infinity of that difference should give us 0. So that's kind of the way of defining slant asymptotes. The way that we actually find a slant asymptote is a little different though, because this doesn't suggest how to come up with the mx plus b in the first place. It just shows how to verify that as a slant asymptote once you have a candidate. So we're going to do an example where we have to deal with that. I want to graph this function, y equals 1 plus 5x minus 2x squared over x minus 2. You have graphed functions like this in pre-calculus or college algebra. It's a normal rational function. And it's nothing fancy, but we're going to look at it from the perspective of calculus here. So start with the domain. This function is not defined at x equals 2, but it is defined everywhere else because that's what our denominator is telling us. So negative infinity to 2 union 2 to infinity. That's our domain. Next up, we want to look at intercepts. Okay. So let's start with x-intercepts. I would set y equal to 0. 0 equals 1 plus 5x minus 2x squared over x minus 2. Multiply both sides by x minus 2. This is the same thing as saying this. I'm going to rewrite this as negative 2x squared plus 5x plus 1 equals 0, putting that in standard form. If you tried to factor this, you're going to find that it does not factor nicely. So we go to the quadratic formula for this guy. X is equal to negative b, so that's negative 5, plus or minus the square root of b squared, that's 25, minus 4ac, it's minus 4 times negative 2 times 1, all over 2a, that would be negative 4. This is equal to negative 5 plus or minus, that's 25 plus 8 right there, which is 33, all over negative 4. So as we've been doing with the examples in this section, we're going to approximate this with decimals so that we can, again, find these points on a graph. This is approximately, where did I write this one down? Approximately negative 0.186 for the minus up here, and then for the plus, it's going to give me approximately 2.686. Okay, so those are going to give me my two x-intercepts. Negative 0.1860 and 2.686. Okay, y-intercepts. We finally have a graph that's going to have a y-intercept. For the y-intercept, I'm plugging a 0 in for my x's here, which is just going to leave me with the constant term in the numerator over the constant term in the denominator, 1 over negative 2 or negative 1/2. I'm going to have a y-intercept at 0, negative 1/2. Okay, so that deals with intercepts. This function also doesn't have symmetry. Sorry, I didn't include an example with symmetry. I actually didn't really even think that I did that until I printed these notes out and started working on this, but no symmetry to look at here. So beyond symmetry, next up we need to look at asymptotes. And this is where we include the discussion of slant asymptote as well. But before we do that, we will have another type of asymptote. So first of all, this thing will have no horizontal asymptotes. And even before you talk about limits, in pre-calculus, you talk about how to determine if that's the case or not. It's going to have no horizontal asymptotes simply because the degree of my numerator is larger than the degree of my denominator. That means that if I take the limit as x approaches either positive or negative infinity, this guy is going to go to either positive or negative infinity. It won't go to any finite number. And you can verify that using the techniques that we did from chapter 2 and how to evaluate those infinite limits. But I'm just going to note that there's no horizontal asymptotes. None. If there's a vertical asymptote, it's going to occur where x minus 2, or it's going to occur at x equals 2, because that's where we're seeing a discontinuity, or a place where our function is not defined. So we want to look at that next. So for vertical, take the limit as x approaches 2 from the positive side of our function, 1 plus 5x minus 2x squared over x minus 2. So for this, what you'd want to do, because this is going to go either to positive infinity or negative infinity, I would just plug in, I would do this one numerically, plug in something very close to 2 but on the positive end, maybe 2.01, and see what happens. You'll get a very, very large positive number in this case. This is equal to positive infinity. If I take the limit as x approaches 2 from the left of the same function, 1 plus 5x minus 2x squared over x minus 2. What's going to happen here? Well, again, plug in a number. Do this one numerically, very close to 2, but just to the left, maybe 1.99. You're going to see that this gives you a very, very large in absolute value negative number. So this is going towards negative infinity. That tells us our behavior near that vertical asymptote. Okay, now as I alluded to before, we should have a slant asymptote for this function. For rational functions like this one, your indicator that you'll have a slant asymptote is when the degree of your numerator is exactly 1 larger than the degree of my denominator. My denominator has a degree of 1, my numerator has a degree of 2, so it's 1 greater. How do we find that slant asymptote? The trick is to actually divide these polynomials. You can either use polynomial long division, or in this case, we could use synthetic division. Synthetic division is definitely the way to go. It's a lot faster. If you don't remember how synthetic division works, you have to have a linear polynomial in your divisor, which is your denominator down here, and the leading coefficient has to be 1, which is the case. For synthetic division, we're going to put a 2 right here. It's whatever you could plug in for that x to make a 0 in that denominator. And then I'm going to write the coefficients of my polynomial, but in my numerator's polynomial, but in standard form. So -2, 5, 1. -2, 5, 1. And then we're going to go like this. I'm going to bring that -2 down, multiply. 2 times -2 is -4. Add 5 plus -4 is 1. Multiply. 2 times 1 is 2. Add 1 plus 2 is 3. And that is going to give me my remainder term. These represent a polynomial, 2x plus 1. So what this tells me is that my polynomial, y equals 1 plus 5x minus 2x squared over x minus 2, is exactly the same thing as this. -2x plus 1 plus 3 over x minus 2. This 3 becomes the numerator that's left in my rational expression. Okay? This is exactly what it's equal to. When you do this synthetic division, everything except for your remainder term, this linear polynomial right here, this linear expression, that guy is going to be your slant asymptote. And here's the reason why. Again, we want to look at the limit as x approaches infinity of f of x minus mx plus b, where mx plus b is the thing that we think is our slant asymptote. That would be this guy. So my function, if I look at the limit as x approaches infinity of f of x minus just that, -2x plus 1. Well, we just determined that f of x is equal to this. -2x plus 1 plus 3 over x minus 2. Then I have this thing, minus -2x plus 1. But look, -2x plus 1 minus -2x plus 1. Those cancel. And then this guy, as x goes to infinity, my denominator gets very, very big. My numerator stays at 3. This will go to 0, exactly like the definition of slant asymptote requires it to. So this means we have a slant asymptote at y equals -2x plus 1. Okay? In homework and stuff like that, you don't need to do this. This is just showing how the definition comes into play here. All you need to do is the synthetic division and then grab everything except for that remainder term there and say that that's your slant asymptote, because it works every time. All right, now we're going to do increasing, decreasing. So we need a derivative. Now, I could use my original function here, where that would require the quotient rule, which is not everybody's favorite rule to use. It gets messy and it can be difficult, especially when you have to do a second derivative after that. However, right here, we did synthetic division and we got an expression that's exactly equal to the original function. So I could just use this and take the derivative of that guy, which is actually a whole lot easier. The derivative of that would be -2 minus 3 times x minus 2 to the -2nd power. That's it. That's pretty straightforward. I set that equal to 0. And then to solve it, I'm going to multiply both sides by negative x minus 2 quantity squared to get rid of this negative second power here. So what that's going to do is give me 2x minus 2 squared plus 3 equals 0. But look what happens. I could try to solve this thing by expanding that out and then using the quadratic formula or something like that, but don't bother, because if I subtract the 3 and divide by 2, I get x minus 2 squared equals negative 3 halves. This has no solutions, because if you square something, you can't then get a negative number. Okay? The fact that there's no solution means there are no critical numbers in this entire function, which is kind of nice. You just need to look at what's happening at your vertical asymptote. So no local maximum, no local minimum values, but we do need to look at our vertical asymptote at x equals 2. Okay, this is where you would just plug numbers into your derivative, which again, remember, that's this thing. Pick something to the left of 2, maybe a 0. Pick something to the right of 2, maybe a 4 or a 5, doesn't really matter. And just look at what's happening to your function. On this side, y prime is going to be less than 0. It's going to be decreasing. And on this side, we get y prime is also less than 0. It's still decreasing. Okay, so even though we have a vertical asymptote there, we don't have a change in our increasing and decreasing behavior. It's decreasing the entire time. Excuse me. Local max and min. We said that there are none. Already established that, so that's cool. Let's check concavity and points of inflection. For this, we need a second derivative, and once again, I recommend using this. Use this version of your first derivative. Y double prime, that constant term is going to go away. I use the chain rule here. I'm going to get 6, chain rule. Let me use chain rule. 6 times x minus 2 there. If I set that equal to 0, to the negative third power. Yeah, let's do that. This thing has no solution because, again, this is the same thing as 6 over x minus 2 cubed equals 0, but this thing can't equal 0 unless the numerator can equal 0, and the numerator is a constant. It's 6. It's non-zero, so it's not going to happen. No points of inflection, okay? But we can still have a change in concavity where the vertical asymptote occurs. So this means no point of inflection. We should still look at this, okay? What happens to y double prime on either side of 0? Once again, plug in something. So for example, plug a 0 in. If I plug 0 in here, I get 0 minus 2, which is negative 2. I'm raising negative 2 to an odd power, so it's still going to be negative. Times a positive, it's still going to be negative. So I have a negative second derivative. Plug in a 3, for example. 3 minus 2 is 1. This becomes 1. 6 times 1 is positive 6. I get a positive second derivative. So we are concave up on 2 to infinity, concave down on negative infinity to 2. Now, I didn't leave myself enough space here to sketch my graph, so I'm going to grab another piece of paper here, which we will use to put all the pieces together. All right, so let's go like this. All right, what do we know? Our domain is all real numbers except for 2. That's fine. We have x-intercepts at a couple of values that we had to round, so let's put those on our graph. See, one of them was negative 0.186. One of them was 2.686, like that. Okay. And then we also have a y-intercept, which we found here at 0, negative 1/2. So let's say negative 1/2 is like here, negative 0.5. Y-intercept there, x-intercept there, x-intercept there. Okay, What else do we know? No horizontal asymptotes, but we do have a vertical asymptote at x equals 2. So x equals 2, I'm going to put that maybe like right here. We have a vertical asymptote there. Okay. What else do we know? We have a slant asymptote at negative 2x plus 1. So we stated that here. Okay. That means we have a y-intercept of 1 on that guy. Slope of negative 2. Now, if I wanted to be really careful about my slope, I would actually put a lot more labels in here so I can make sure that I'm going down 2 over 1, down 2 over 1, and so on. But because I'm already including these decimal values here, and I don't want to clutter things up too much, I'm just going to make sure that my y-intercept is correct and make sure that I have a negative slope that's relatively steep, because the slope of negative 2 is relatively steep. And I'm going to just say that this is the line y equals negative 2x plus 1. So I know that that's my slant asymptote. Okay, we have that. Now, increasing, decreasing. So we are decreasing everywhere to the left of 2. And we also know that everywhere to the left of 2, we are concave down. So to the left of 2, we are decreasing and concave down, and we pass through these 2 points here. That indicates that this thing is going to do something like this. Not like that. Okay? And I drew that really, really badly. It actually appears to change concavity, which it should not. It should be concave down this entire time, and should approach this slant asymptote this direction and this vertical asymptote this direction. Then we also know that our function is decreasing to the right of 2, but concave up. So that means that we are doing something like this. Okay? So approaching the vertical asymptote to the left, approaching the slant asymptote to the right. Okay? So not a good graph. My graphs tend to not be good anytime I do them by hand, but that's what that would look like. Okay? And that's going to wrap our section up.